All right, hello everyone. Welcome to the Cambridge University Astronomical Society's Weekly Talk. I'm Xavier, the chairperson of the society. Tonight we have Dr. Ziri Younsi with us to give a talk titled "The First Images of Black Holes from the Event Horizon Telescope: Past, Present, and Future." Before we begin, let me share a little more about our speaker. Dr. Ziri is a UKRI Stephen Hawking Fellow at UCL. He obtained his MA in mathematics from Cambridge in 2006, followed by an MSc in physics at UCL in 2008, and completed his PhD in 2014 at the Muller Space Science Laboratory at UCL. He is one of just 2 scientists at the Event Horizon Telescope team, and in 2019, the team unveiled the first direct visual evidence of a supermassive black hole and its shadow. Now, without further ado, Dr. Younsi, please.
Thank you very much, Xavier. Thank you, everybody. It's a genuine pleasure to be here today, to my alma mater, where I matriculated back in 2003 now, and I think I did my first year exam here. So fond memories indeed. Thank you, first of all, to the organizers of this Cambridge University Astronomical Society meeting for their kind invitation and their hospitality this evening. It's a pleasure to talk about something which I, in a sense, began my research on as an undergraduate student here, namely black holes. And so the title of my talk this evening is Past, Present, and Future of the Imaging of Black Holes in the Context of the Event Horizon Telescope, which is this collaboration with this logo here in the bottom left that I've been working in since 2014. And what you're seeing in this title slide image here is actually a synthetic calculation. So it's a synthetic image. It's a calculation informed and data driven of what the black hole in our galactic center would look like. So it's a simulation, but it's based on best fit parameters. And I hope by the end of my talk this evening, I've given you some flavor of how we go about doing this and how we try and reconcile theory with observations and how we try to drive these observations and interpret our observations on the basis of theoretical predictions like these. So without further ado, I'm going to jump straight in and say this is the image. And so this is the focus of the discussion this evening. What does this image mean? And so before we get into the sort of details of the science, a little bit of a diversion. So social media was very, very keen to interpret this image. And on the day, we were really actually overwhelmed as a collaboration because we've been looking at these kind of images for years, and this particular image since 2018. We were overwhelmed by the media response to this, and it's featured on the front pages of practically every major newspaper around the world. And if I recall, the global reach of this was over 3 billion people had seen this image that day. And so people asked, what does it mean? And social media was very quick to respond to this. And so what I'm showing you here are 3, what I think of as fundamental tenets of human nature represented through these social media pictures. So the first is fear in the eye of Sauron. The second is food. And coming up now, so the giant cosmic bagel, my favorite, is the giant cosmic kitty cat. This is my favorite one. There we go. Of course, what's wrong with that is there are 2 black holes. So we have fear, we have food, and we have felines. So fundamental tenets of human nature. So as fun and humorous as these images are, they also, I think, represent just how deeply these images that we published in 2019 actually resonated with the general public. A lot of people had a lot of unanswered questions. And the image, so just to say that the color scheme, that isn't the actual color. It's a radio image. It's a reconstruction from a radio image, and I'll go into that later this evening. And the color is what we chose because it's perceptually uniform in brightness, and the red is quite exciting. So, and white is the hottest material. So what I'm going to do today is pose a few questions, and the structure of this evening's talk will be centered around these 4 main questions or themes. And the first is, what is a black hole? Because I appreciate that not everybody here is familiar with black holes, either in nature or in terms of a prediction or even a solution of the Einstein field equations in Einstein's theory of general relativity. And that is the sort of bedrock, because we need to perform theoretical calculations and generate predictions of what we would like to, what we think we are going to see in order to compare this with the observations that we've now recorded. And once we've addressed this, we have to determine where we should look. because the universe is a big place and the angular size of a black hole is actually extremely small. And we want to resolve things on the scale of the event horizon of the black hole. So there aren't actually many sources at present which fit the bill and are within the angular resolution of an instrument like the Event Horizon Telescope. So once we've determined where we should look, the next thing is to determine how we can see it. So do we just build bigger and bigger dishes? I mean, I think most of you already know we constructed an array of telescopes, and I'll go into that. And finally, what do we learn from this image? And this is, in a sense, what we as scientists are charged with doing. And this is what the general public has been asking for a long time. And so I will provide some interpretation of what we see based on this result that we published in 2019, but also based on some results that we published just in April this year on the polarization of light that's observed from this black hole. So jumping straight in, what I'd like to do first is provide a very brief history of black holes, because when I first started looking into this back in 2018, I was surprised by how far back in time the concept or the notion of a very, very compact object existed. And in fact, it goes back all the way to 1783. The chap called Reverend John Michell, who was a polymath, and I think he was actually a fellow at Queen's College here in Cambridge, who proposed this notion of a dark star. So the prevalent theory of gravity at the time was Newton's theory, and there was this notion of the corpuscular theory of light, and he posited and he considered an object that was extremely dense. In fact, it was so dense, so compact, that its surface gravity was such that not even, so like a star, that not even the light that this dark star radiated could escape its surface. And he called this a dark star. And actually, Pierre-Simon Laplace came up with effectively the same idea a few years later independently too, but Michell was there first. But this fell out of favor pretty quickly because we had Thomas Young and his double slit experiment, and then there was this whole issue with the, what was eventually reconciled with quantum mechanics and the wave-particle duality of light. And so this was forgotten for a very long period of time. And so fast forwarding to 1915, we, of course, have Albert Einstein himself, who 10 years after his theory of special relativity, presented his theory of general relativity, his theory of gravitation. And one of the crowning achievements of that theory is a set of equations called the Einstein field equations, which at the time so they are basically a system of very complex partial differential equations and very hard to solve even on supercomputers today. It's an industry. And no one thought that there would be any analytic solutions to this. But in the same year, published early in the following year, in 1916, Carl Schwarzschild published his solution. They weren't called black holes at the time. They were just thought of as like a stellar object of sorts, a non-rotating solution. So this was what would later be known as a black hole, and it had only mass. It didn't have any spin and it didn't have any charge. So I should say that black holes can be wholly characterized in terms of only those three parameters. So they're relatively simple objects in that sense. So Carl Schwarzschild came up with this solution. He sadly died not too long later, so he didn't have a chance to work further on this. And in the years that followed, there were lots of tremendous breakthroughs in understanding the structure of black holes, the mathematical properties of them, extending this to black holes with spin, like the Kerr solution. And I skip over all of that because that's an hour presentation in itself, perhaps more actually. But there was a chap called John Archibald Wheeler, who can be thought of as the godfather of gravitation. He published what we call Misner, Thorne, and Wheeler, which is like the Bible of gravitation to people who actually work in this field. And he came up in a meeting at the American Astronomical Society of the term black hole. And since then, the term stuck. But just to say, I think that it's a misleading term because a black hole isn't actually black. It can, as you probably many of you know, can radiate a minuscule amount of black body radiation in the form of Hawking radiation. And it's also not a hole because a hole you can fill, whereas a black hole, as you dump more matter into it, it will actually grow. So it's misleading, but nonetheless, the term has stuck. And I just wanted to give a little bit of that background. So moving closer towards present day. In the years that followed, there was a lot of indirect evidence for the existence of black holes. So one of the key things about this observation and this measurement by the EHT was that until then, black holes existed as a concept, as a notion, as a means to explain a variety of astrophysical phenomena, but there was no direct evidence for their existence. And so we had things like the detection of radio pulsars by Jocelyn Bell Burnell, We had observations of high energy X-rays from systems like high mass X-ray binaries. So this would be like a stellar mass compact object, like a black hole that's accreting matter from a nearby companion star. And of course, we have the stellar motions in the center of our own galaxy. And this was actually awarded the Nobel Prize, well, half of the Nobel Prize last year for observing these motions, in particular some of the stars like S02, which were observed. So in this movie here, this is the center of the galaxy where a purported black hole resides. And these objects that you're seeing orbiting around are actually stars. They're not comets, they're actual stars moving on highly eccentric trajectories. And of course, you can use things like Kepler's laws, and you have multiple observations, and some of these stars orbit for multiple orbits. You can infer a mass, and the mass can be constrained to be of the order of 4.5 million solar masses within a region smaller than the orbital radius of Mercury, I believe. And so that's quite compelling proof that there is something extremely compact residing there. So that's in our galaxy. So there's a lot of indirect evidence. It almost certainly is a black hole. Only a black hole could be compact enough to present these sorts of orbits of stars. Only a black hole could power these prodigiously high energy emissions from the centers of other galaxies, and so on and so forth across the entire electromagnetic spectrum. But nonetheless, it's not direct proof. And then, of course, in 2015, we had the detection of gravitational waves, which in my mind is a truly remarkable result, because this is something that even Einstein himself didn't believe truly. He wasn't comfortable with this, amongst other things. He wasn't comfortable with gravitational waves, but they were detected by LIGO-Virgo collaboration as ripples in space-time. And space-time, which is Einstein's concept of the fabric of reality, of space and time being unified into a single framework that can describe all of this, which I'll come to in a moment. And gravitational waves are ripples in the fabric of space-time and the fabric of reality itself, in a sense. And these were detected, which is truly remarkable. So it's an important experimental verification of his theory, and it's still going strong. And finally, of course, we have the first image, and I say image in quotation marks, and I'll come back to that throughout the talk, of a black hole by the Event Horizon Telescope. So now, the first thing in terms of understanding this image is to understand theoretically what a black hole is. So, you know, this is, I appreciate, a very, this is a public talk, so of course we're not going to go into the mathematics and the theory of general relativity and so on. But I think what might be the only equation I show in this talk is the following, and I'll talk you through it very briefly. It's actually an extremely elegant equation, and it's can be understood as follows. So you have a left-hand side G, and you have a right-hand side T, and they're proportional to each other. And so this left-hand side G describes the geometry or the structure of space-time. And space-time is this fabric. So Einstein's realization and his you know, one of his crowning achievements was coming up with this realization that space and time can be treated on an equal footing. And in so doing, he constructed a framework wherein things like the precession of the perihelion of Mercury, the deflection of light by the sun, and numerous other tests since, mostly in the weak field regime, could be understood. And he said, okay, everything should be described in terms of space and time. Time is not special. Time is special to us. There's an arrow of time. It seems to point forwards. We have no control over the other three dimensions. We have some control, some semblance of control. But the universe doesn't care about that. Space and time need to be treated equally. On the right-hand side, we have what is matter. So this equation is telling us that space, time, and matter are related. So space-time is the fabric of the universe, and matter is all the stars, dust, gas, us that lives in space-time. And this constant of proportionality tells us that there's a dynamical feedback. So for example, you could change the distribution of matter, and you can make an object more dense. What that will do in turn is cause space-time to become more curved. And so the curvature of space-time gives rise to gravitational forces, as opposed to Newton's theory, which says that, you know, there's action at a distance and all this sort of thing. So it's a radically different way of understanding the universe and its mechanics and dynamics and so on. And, you know, it goes well beyond just black holes. There's cosmology and many other things. But tonight, we're just talking about black holes. And so it's a really remarkable thing. And so you start to see things like the deflection of light from distant stars. So in this image on the left here, in the center, you see a star, not too different from, say, our sun. And here we have Earth, where we're recording starlight. And so here we have A, the actual location of the star, and B, the apparent location of the star. And Einstein's general relativity is extremely successful, for example, in detecting the deflection of starlight. And the angle of deflection is something which can only be predicted within his gravitational framework. It's not something that can be accounted for within Newton's theory, for example. And there have been many other verifications of this since. So we need Einstein's theory for this. We need Einstein's theory for GPS systems in order to record our position geolocated accurately in space and time. So general relativity is actually a cornerstone of modern life, and not just modern physics. So anyway, Einstein did a wonderful thing in determining this, but black holes are quite simple objects, and because they have an event horizon, they trap all light which crosses that event horizon. You can't actually see a black hole. But what you can see is light which is produced and emitted very close to its event horizon. So in order to understand what a black hole would actually look like if we were able to observe it, you need to understand more its environment. And so here's a very simple picture. And in the center, we have the black hole itself. And so we have the event horizon, so this black boundary. Interior to this event horizon, we have a singularity. I'm not going to talk about that here today, but it's where effectively the equations break down, the mathematical description of black holes break down. And so that's why a lot of people are interested in understanding what happens near and inside the black hole event horizon, because that probably is a viable path towards something like a quantum theory of gravity. And gravity is very hard to quantize. In fact, no one's been able to quantize gravity. And so the unification of a gravitational field theory and quantum field theory is something that's an outstanding problem in modern physics. And what's going on within there is probably intimately related to that. That's not something we're going to talk about today, but we don't understand much of what happens beyond this event horizon, but nor can we see beyond it anyway. But what we do care about is the matter which is swirling around the black hole, because a black hole has a tremendously powerful gravitational potential. And so matter, say from a nearby star, can slowly be accumulated onto the black hole, and it can gradually flow in through a process of basically loss of angular momentum. And as it falls in slowly, there are various dynamical effects at play. For example, viscous forces. There are things like dynamical friction, and this matter starts to heat up. And as it heats up, it becomes hotter and hotter, and it becomes ionized. And ultimately, at the end, it can become so ionized that it's basically a plasma of just free charges, and it's incredibly hot, and it's radiating energy across the entire electromagnetic spectrum. And the goal of a project like the Event Horizon Telescope is to detect the light produced by matter very close to the edge of the event horizon. And in so doing, you can actually construct a shadow of the black hole, and I will show that shortly. And we do also see things like relativistic jets, which are very much intimately related to the magnetic fields that are inside this accretion disk, and coupled with the black hole in ways that we're not, there's no definitive understanding of which processes do this. So there are some very strong contenders for this, but we see relativistic jets around black holes, which we think are spinning extremely rapidly as the magnetic field gets wound up, and I'll show simulations of that shortly. And we see that, for example, in systems like in Messier 87, which is where the EHT took an image, but at the wavelengths that we're interested in, this is actually optically thin, and we just see the matter here. So this is the environment that we see that the black hole typically lives in. But this is misleading. This is not what you would see, because the gravitational field is so strong that even light is bent by the black hole, and the light can orbit around the black hole. It can perform multiple orbits around the black hole. You could stand near the edge of a black hole and you'd see multiple images of the back of your own head. So you're not going to see this. And so the question is, what are we going to see? So I'm going to pick up the pace a bit now, because I started a little bit slowly. And so here's a movie that we produced in the EHT project of what this would look like. So this blue mesh is a sort of embedding. So it's a sort of lower dimensional representation of the space-time structure. Think of it as like a two-dimensional sheet when viewed from above. And this red here, this boundary, is the event horizon of the black hole. Now we're going to fire light rays. So this one passes quite close by the black hole, it's bent slightly. And as they pass closer to the black hole, they're deflected through larger and larger angles. Now, as we rotate our field of view, you can see at the center, there's infinite curvature, that's the singularity. And then we approach a limit, like a sort of continuum limit, where we're firing more and more photons, light rays. We have what we see here, and we can actually record these photons, much like pixels on a CCD, or collect them on a photographic plate to be more traditional, but record them we do. And in the most simple case of isotropic emission, which is of uniform intensity and so on and so forth, a homogeneous distribution of matter, the black hole isn't rotating or anything like that, you'd see a perfect dark circle with a roughly 1 / distance squared drop off in intensity from the edge, a little bit like an eclipse. And this shadow is effectively the projected image of the capture cross-section of the black hole's event horizon. The event horizon itself is somewhere in here, but there are light rays which pass close by, and there's a sort of critical impact parameter where light rays which pass too close to the black hole would swirl around and eventually drop in. And so this is what we see. But unfortunately, nature is not so kind as to provide us with such perfect systems. Nature is much more complicated. And so what I'm going to do in the next few slides is show you how we can build up from this basic principle a better understanding of what a realistic image of a black hole around, for example, in the galactic center or in Messier 87 would look like. So using this as a starting point, there we go. Let's look at what happens if we put a simple but non-isotropic spherical distribution of matter around the black hole. So what we can do, first of all, I should take that back, sorry, is we first consider the properties of light, and we don't consider any matter around the black hole, but only the behavior of the light. So what you're seeing here is effectively a sphere that's colored into 4 quadrants. So pink, green, yellow, and blue. And this cutout here just shows you that around the equator, around theta is pi/2, there's a white circle, and that'll become relevant in a moment. And so we can put a black hole in the center there. But what we're going to do, apologies. Oh, there we go. So there was an arrow which started at the North Pole and it moved down to the equator. That's us as an observer, just on the interior of this surface. So we're not on the surface, we're sort of inside looking towards the center and always directed towards the center as we move down from the North Pole to the equator. So what would we see if there weren't a black hole and it was just empty space, normal flat space-time, so to speak? We would see the following. You would see some warping, but that warping is just geometrical distortion caused by the curvature of the sphere itself because it's at a finite distance away from us. So you see nothing except this changing field of view. And you see the white circle there at the equator. And then we move down to looking towards the North Pole because we're moving from north to south. But what happens if we put a black hole, a rapidly spinning black hole this time, at the center of this sphere? And we see the following. So you see this dark circle where the shadow is. You see multiple nested lensed images of these different regions. So you see not 1 or 2 yellow regions. You actually can see, if you look really closely, 3 and more. There's actually an infinity of these because photons can wind an infinite number of times around the black hole. And so if we freeze the frame at the equator, so looking edge on at the black hole itself, we see this asymmetric profile. So now you see that the black hole shadow, if the black hole itself is spinning, is asymmetric. So if you see a black hole that's asymmetric like this, it's highly likely that it's spinning. But what you also see is what I mentioned earlier. You see, like, for example, a blue patch here, and then a blue patch here, and then a blue patch here, and there's an exponentially decreasing amount of surface area of these. And you can think of these as like quadrants of flux in the sky. And you get this sort of successive pattern, this buildup of, and so when you look at an image of a black hole, you're not going to just see a conventional image. You're going to see entire regions of the sky warped and lensed and magnified and stretched and so on. And it's quite odd, but most of all, you see this white ring, what was the white circle, which would be directly behind the black hole. and you'd never see it typically because of the black hole's gravity. It's bent into our line of sight. So those photons which are emitted from the ring behind the black hole away from us are bent by the gravitational field of the black hole back into our line of sight and lens into a ring, a perfect ring in the special case where we're looking at it edge on. There we go. And so the next question is, we have some feeling of what's happening with light, but let's visualize this using something a little bit more realistic. So we're going to paint a star field. So this is a calculation where I took a realistic survey of stars and mapped them onto a sphere very far away from the black hole. And now what you see as we fade in, you still see the shadow, but now you see the actual stars, and that white ring is actually like an Einstein ring. So this is so that's a small region of stars far behind the black hole, which are lensed, gravitationally lensed by the gravitational field of the black hole to appear much more extended and bright than they otherwise would. In fact, you'd never see them. And you see this sort of warping substructure. So this stuff here is the light emitted over here, here would be here, and so on. And so it's important to have these like simple colored patch models to kind of gain an intuition as to what we're actually looking at, right? And so we call this the black hole shadow. And this is the Einstein ring, which I've already said. And so this is sort of the building blocks before we start to say, okay, now let's put a realistic matter distribution, because of course the background starlight would not be this bright. And what we expect to see is an accretion flow, but those accretion flows are actually quite complex. They're highly turbulent, they're highly relativistic, they're highly magnetized, and so on. Everything's dialed up to 11, right? It's extremely extreme. So let's start first by considering a simple geometry, a planar geometry, a disk, an infinitesimally thin and optically thick, so it's opaque disk around the black hole, which is in the center here. And let's have our photographic plate, or CCD, recording the photons that are produced. Now, photons which are produced on the near side of the accretion disk come almost directly towards us, and they're not really affected significantly by the gravitational field of the black hole because they escape it directly. But those photons which are produced on the rear side of the disk are bent and, for example, emitted away from us. If you look at, say, the tangent to this, they're bent into our line of sight and recorded because of the gravitational potential here, the gravitational field. But more bizarrely, you get photons that are emitted from the near and the rear underside of the disk, which also bent into our line of sight. And so if you imagine you looked at a thin disk, or like, for example, a record or a CD edge on, you just see a horizontal line with some thickness that's the thickness of that disk or that record. But when you look at a black hole image, you see something very different. You see an apparent warping. So it looks like this, three-dimensional distribution of matter, even though it's actually a purely two-dimensional distribution of matter. So you see an apparent warping of the rear side, and you see a sort of warping here, which is actually the same as the underside of this part of the disk. And so it's quite counterintuitive. And so Hollywood has actually looked into this, and I think many of you have probably seen the movie Interstellar, directed by Christopher Nolan in 2014. And actually Kip Thorne, Nobel Prize winner, was the scientific consultant for this film. And this is their rendition of an accretion disk, which is not too dissimilar to the one I just showed you that you can calculate on my laptop, for example. But it's as beautiful as it is, it's misleading in several ways. First of all, it's uniformly bright. Now, this black hole is actually spinning, and as such, the approaching side here would actually be brighter because that radiation is Doppler boosted and appears brighter, beamed into our line of sight. And this receding side, which would be moving away from us rapidly, would be conversely dimmed. And so you'd see an asymmetry there, for example. And so it wouldn't really look like this. And the second thing is that actually, you don't tend to have, for example, in the centers of galaxies, disks which are very thin like this, around supermassive black holes. They tend to be quite puffy, and there are radiation forces and so on. And so the matter has some vertical extent too. And there are many other things besides, but nonetheless, it's a great movie, and it's a beautiful picture. Actually, the first, if you will, scientifically accurate image of a black hole and its shadow and the flow around it was performed by Jean-Pierre Luminet. And he published this actually in a popular science magazine in Paris in 1978. The actual paper was published in 1979. And this is his rendering. And what he's done is each pixel here is an ink spot, India ink on a photographic plate, and he took the negative of this. And so back in 1978, computers weren't nearly as powerful as they are today. My smartwatch is a lot more powerful than the computers that he had, all of ours would be, all of our laptops and phones and so on. So each of these was a painstaking calculation. He took put a lot of time into this. And this is what it looked like. And what's accurate about this in part is that the left side that's approaching us as the black hole spinning is now brighter, as I mentioned earlier. So this goes back to Luminé. That's the first known calculation of this that's published. But things have changed, and we've moved on a fair bit since then. And now we have these technologies and these instruments like the Event Horizon Telescope. We have to construct more accurate models. And thankfully, we have supercomputers now, which are pretty powerful. We can do a lot. And so we can do things like actually put a realistic accretion flow. And so this is a supercomputer simulations, what we call a general relativistic. So that's Einstein's theory of gravity, magneto-hydrodynamics. So it's hydrodynamics of plasma that's highly magnetized in curved space-time. And it's a fancy way of basically saying we solve the equations of hydrodynamics with magnetic fields around a black hole. And when you do this, and it's computationally expensive, and it's something that's only been possible to do to these kinds of resolutions in the last decade or two, you can perform these simulations, and then you have an accurate time evolution in 3 dimensions as well of the flow of this magnetized plasma around a black hole. And then you can take a snapshot of this, and you can calculate the trajectories of light rays, and you can produce an image. And this is what you see, and you see this approaching side is brighter. You see wispy things here. This is actually the base of a jet, and I'm going to explain what all of this means shortly. But this is effectively the state of the art. And these are the sorts of images that we want to compare with EHT observations in order to try and extract things like the mass, the spin, and other fundamental parameters of the black hole and its surroundings. So here's just a quick movie that I made. And so you feed these simulations into what we call radiative transport calculations. So you have to take into account the thermodynamic properties of the intervening medium. So that's the plasma around the black hole. That could be the interstellar or the intergalactic medium. There's scattering processes. You have absorption, emission, scattering. You have polarization of light. You fold all of this in, and when you solve all of this on a computer, you can calculate things like this. And this is just the observer field of view moving around as we look at this thing. And this black hole spinning extremely rapidly. And what you've seen is first flying around from the North Pole to the South Pole and back again, and then we're moving around. And now as we move from North to South Pole, you probably saw, let's just wait one moment. When you view the black hole down the spin axis face on, it's uniformly bright. Now, as you move edge on again, you see the brightness asymmetry shifts to the left side, which is the side which is approaching us because this black hole is spinning. And this is a sort of realistic image of a black hole. If you had perfect infinite resolution. So, but alas, we don't. And so now we have some idea of what a black hole, at least the prediction of the image of a black hole based on Einstein's theory of general relativity, based on our understanding of the behavior of matter in this regime, we are ready to start looking for a candidate. And this isn't an easy thing to do. It's something which has kind of theoretically been understood for a long time, but it wasn't actually until a paper in 2000 by Falker, Messier, and Agol was published, which actually said, you know what, it might be possible to resolve an image of the black hole in our galactic center. Barely. We could achieve a resolution equivalent to the diameter of this black hole, or thereabouts, in the next 10 to 15 years. And this is effectively what's happened. But before that, it was just considered complete fantasy. And so there are 3 things you want in taking a picture of a black hole. The first is that you want, of course, this black hole to be as large as possible. By that, I mean, you want it to have a physical size. That event horizon should be as large as possible, because that would mean that its angular size on the sky would be maximal. And of course, you want it to be as close as possible, because ultimately you want that angular size. So that's the ratio. So a black hole's diameter is effectively proportional to the mass alone. So you double the diameter, you double the mass, you double the diameter of the black hole. You want it to be as close to Earth as possible, so the ratio of the mass, so of the size of the black hole to its distance is maximal. And finally, you want optimal observing conditions, which is an umbrella term for all sorts of nasty things, which I'll touch on one or two in a moment. So you want to optimize these. And so what the EHT does is look at candidate sources. So far we have two, and the first is this nice looking galaxy here. This is actually a simulation. This is our galaxy. This is Sagittarius. This is Milky Way and Sagittarius A stars, the supermassive black hole, which resides, we believe, right in the center here. We're in the fortunate and unfortunate position of living at the edge of one of the spiral arms. And what that means is we have to look, and we live in the plane of our galaxy, roughly, that we need to look for all of that intervening dust and gas to see that black hole. And of course, here's a picture of M87 with its prodigious jet originating here from the top left. This was actually, I think, first observed in, I think, 1918 by Curtis in the optical. So it's been known for a long time. And so going by these three parameters, of course, mass, where we see that M87 is more than 3 orders of magnitude larger in mass, more than 1,000 times larger in mass. So it weighs 6.5 roughly billion times the mass of our sun. So looking at that, you'd say, okay, that's great. But in terms of distance, if you compare the two, M87 is also more than 3 orders of magnitude further away. It's 55 million light years or so away, which is pretty far indeed. So if you look at the ratio of the mass to the distance, they're effectively comparable. But what really kills it, and that is why the first result that was published by the EHT was of M87, is that because M87 is an extragalactic source, you just look up and you don't have to contend with things like the interstellar medium and the difficulties with some of the effects that come about because of this. So one of those is actually the fact that light is refracted and scattered quite rapidly. And there's a frequency dependence in this, observing frequency dependence. And so those images are extremely blurred, basically, of our galactic center black hole. And the other thing is, because this black hole in our galaxy is roughly 1,000 times smaller in mass, it's the time scale over what physical processes that occur near it happen. So how that matter that swirls around the black hole reorders itself happens 1,000 times faster. So for M87, the typical timescale is of the order of 8 hours to a few days. For our galaxy, it's seconds. So this is like trying to take a picture of a parked car, and our galaxy, galactic center black hole Sagittarius A starts like trying to take a picture of a rapidly speeding car, but not even like a car in the UK. It could be like a car on a German Autobahn, but there's no speed limit. So you're going to end up with something very blurry. And so you have to contend with all of these difficult things. And that's why we focus as a collaboration on this black hole first, because it's like a warm-up exercise. That's what I'll talk about mostly today. So now we run these simulations, but ultimately, how do you actually observe this thing? So you look at radio waves, and I'll explain why in a second, but here's a simulation. The black hole is the sphere here in the center, and we start with an equilibrium configuration of matter, and we perturb it. So we perturb the magnetic potential of this, and over time, instabilities develop, matter starts to accrete onto the black hole. When you run it for longer and longer times, you see a jet develops and forms, and we see jets. You actually see 2 jets in the simulation. There's a counter jet extending the other direction, which isn't seen here. And you see this turbulent accretion flow. And once you've run it for long enough, you effectively can't recover the initial conditions of that setup. You have something which kind of represents a sort of quasi-stationary state. So something which is somewhat representative of the turbulent dynamic properties of matter around the black hole, something which you can use as a basis to model what is happening around that black hole and calculate images. So fire light rays through there and determine their trajectories. But actually, if you zoom in onto a microscopic level, then what you would see, so these electrons are gyrating around these magnetic field lines here in blue. And as they gyrate, they radiate away some of their energy in the form of what we call synchrotron radiation. And this is typically at radio wavelengths. And so taking a picture of a black hole is effectively is about tuning in to these wavelengths. And a typical wavelength is around 1.3 millimeter. That's what the EHT is particularly sensitive to. And 1.3 millimeter is actually very long, right? Or you can think of it conversely as a frequency of 230 gigahertz. And there are, of course, many reasons why radio wavelengths are so useful, not least withstanding that we use them for communications here on Earth precisely because they are weakly attenuated by intervening media like the atmosphere, even mountains and so on. And so what you do through tuning in is you have your radio telescope. And there are several details when you look at your source that are important, but it boils down to two. So you receive your signal, and there are effectively two things that you need to optimize in order to resolve this source, this black hole, as best you can. The first is the size of the telescope, and the second is the observing wavelength. And so effectively, there are all sorts of constants of proportionality that are related to the atmospheric effects and so on, but it's effectively the resolution, and you want to have this as large as possible. You want to maximize the size and you want to minimize the wavelength. So you want to observe at shorter and shorter wavelengths, and you would like bigger and larger collecting areas. You want a telescope or a dish as large as possible. Now, of course, you could naively think, okay, let's build the biggest possible telescope we can. And so here's a radio telescope. It's the NRAO in Greenbank. And they tried to do this. And this is what happened. So, you know, there are fundamental limitations to what we can build here on Earth, just based on our surface gravity, on the materials that we have available, the complexity of the engineering. You know, systems engineering is a discipline in itself, and this is a highly complex thing to build. So we're not going to be able to do this just by building bigger and bigger telescopes. Looking at the denominator of that equation you just saw, we can also push to shorter and shorter wavelengths, which is the same as pushing to higher and higher frequencies. So here's a black hole image that I calculated at a frequency of 23 gigahertz. So this is actually at quite a long wavelength. And what I'll show you now is a succession of images as we increase the, decrease the wavelength. So we make that numerator smaller and that resolution larger. So now, here you go. And now you see already that there's less obscuring matter. So if I go back again, you see it's mostly dark. And that's because the matter is absorbing all of the light and you're not really detecting anything at all because it's self-absorbed. And as you increase the frequency, decrease the wavelength, that matter becomes more and more optically thin. You can see deeper through that material and closer to the event horizon of the black hole. And now we're at the EHT's target frequency. This is what we achieve at the moment of 230 gigahertz, wavelengths of 1.3 millimeters. You see things like this. So you can actually pretty much see the shadow of the black hole. You can see the left side is very bright because it's approaching us. The right side is dimmed. Now this is in a linear scale. In a logarithmic scale, you'd see the contrast ratios of the order of 10 to 100. And you can actually observe that. And in the future, we'll push to wavelengths like 340 gigahertz, actually 345, I should say. But so in the future, we'll be able to do this. And actually, when we move to space, we'll be able to do better still. And you'd see an almost perfect ring in a logarithmic intensity scale. So the point is that you can push to shorter and shorter wavelengths. But of course, the problem with that is that the atmosphere of the Earth has a very narrow window where it's optically thin enough that we can actually detect that radiation, record it, and it's not so attenuated by the atmosphere that it's scrambled. And so there are limitations. So this is an example of what you would see. Now, the question then is, what kind of angular resolutions would we need? So let's say we could build a telescope as large as the Earth. What kind of angular resolution would we need? Well, for a sense of scale, the angular size of the moon at apogee, when it's full moon, of course, is of the order of 30 minutes of arc or so. Now, the question is, looking at this black hole image here, how large is this? And it turns out that it's around 40 microarc seconds. And to give you a sense of scale, I don't know if this is clear to everybody, and I think everybody here sort of roughly understands angular scales. The size of the shadow of the black hole in M87 is of the order of 40 microarc seconds. And so that's of the order of 1/90 millionth of a degree, as opposed to half a degree, which is the angular size of the moon on full moon when it's closest to the Earth. And the EHT actually achieves a nominal resolution that's roughly a factor of 2 smaller than this. And that's remarkable, and I'll explain how in a second. But to give you a sort of sense of scale, it might have been in the abstract of the talk, but it's akin to, with your naked eye, being able to resolve an orange on the surface of the moon from here now, or to resolve individual atoms in your own finger. That's the level of sensitivity that's required by an instrument like the EHT. And so it's, of course, first and foremost, it's an unprecedented feat in engineering to be able to do this. And so next, understanding the sense of the scales and the resolutions that we need, how do we do this? Okay, that's good, that's muted. So this light, this radiation is produced, these radio waves from the black hole. It travels this cosmic distance of 55 million light years. And as it passes through the Earth's atmosphere, it's recorded at not just one, but actually at multiple telescopes around the world. And so what these telescopes do is they record the precise arrival times, and they are networked through a technique called very long baseline interferometry, which I'll outline in a moment. And those precise arrival times are recorded using hydrogen lasers, so atomic clocks. So they have an accuracy of better than 1 second in something like 100 million years. They're pretty accurate. And that's, once they're recorded, that data is shipped from each of those telescopes because they're recorded on hard drives, because it's phenomenal amounts of data. So in 2017, the EHT recorded around 3.5 petabytes of data. That's been going up by almost an order of magnitude with every observing run. And so that's such a large volume of data, you can't transmit that wirelessly. So they have to be recorded physically. And so what happens then is the EHT takes all this data and it reduces it and it correlates it and it stitches it together through this technique of very long baseline interferometry. And effectively, you can synthesize an image which is akin to having a telescope as large, or a telescope which recorded this data, and this telescope is as large as the largest distance between any two telescopes on the Earth. So for example, you could have one in the far northern hemisphere, one in the far southern hemisphere on the precise opposite side of the world, and you'd be recording that data once you stitch it together through this technique, as though that telescope was as a diameter of the distance between those two. And now that sounds quite fantastical, but it's actually a technique which has been around for decades. It's just that this has been extended to intercontinental baselines, which is what the EHT has done. And this is a technique called interferometry, which is also what's used, effectively the same principle in the detection of gravitational waves, but we've done this with radio waves. And so, just to show you a few of the telescopes in the array itself, there were 8 in total, 7 which actually recorded the data, and 8 from the South Pole here. This was used for calibration, so we looked at a nearby quasar source to calibrate. And what you see here are triangles. And the trick with interferometry and taking pictures of things like black holes is you want to form as many of these triangles as possible. And you want triangles which extend across large baselines, so very large separations across the Earth. And you also want smaller triangles as well, because this isn't like taking a traditional image. You're recording radio waves, and those radio waves arrive not as discrete photons, but as diffraction patterns. And you have to match these diffraction patterns. And so what we've done with these, it was 8 telescopes, but 7 which recorded the data. You could see the Earth rotates, but not all of those telescopes are observing all the time, right? So some are on source, some are off source, and you only have a few nights per year where you can have the simultaneous observing time on all of these different telescopes working together to do this. So we only had 4 observing nights spread across, I think, 7 days to do this. And so what I'll show here, and it'll loop a few times and I'll explain. What you see on the left are the telescopes within the EHT array. And what you see in the center here, because like I said, these aren't discrete photons, these are radio wave interference patterns. And there's a thing that we call the UV plane. So you can think of these in a sense like Fourier components of those waves. And this UV plane, the aim of the game here is you want to cover all the white space basically. And what you see here, these tracks, so you probably saw that these different telescopes, they have different colored connecting lines or baselines, and they trace arcs in this UV plane. And those arcs are just as a consequence of the rotation of the Earth, as that telescope is looking at, in this case, M87. And you can see that it's a very sparse coverage of that entire space. But if you look on the right here, as you observe for longer and with more telescopes, the quality of the image actually improves. Now you see a dimple, which is where the horizon is, the event horizon, and so on. And it's not great, but nonetheless, it's actually something that looks not too dissimilar from some of the images that you've seen, including the EHT's one. And this happens when some telescopes like ALMA in Chile, which is the cornerstone of this, the EHT array, comes on board. So these different telescopes, they have different sensitivities. And so the idea is you don't want telescopes which are just as far apart as possible. So when they're far apart, you resolve structure near the horizon. You also want them to be quite close together to resolve structure further away as well. And that's because you want to have a balance of coverage of this space in order that when you take the inverse Fourier transform of this to construct an image, so in inverse Fourier transforming it, you also have to take into account things like the atmospheric properties of each array, of each telescope in the array every night. And there are all sorts of things which are folded into that, which we can't go into here, but you can reconstruct an image, and this is how we do it, basically. So we look at these interference patterns of radio waves, and we try to cover as much as possible, and then we inverse Fourier transform. But however, this is not a well-posed problem in the sense that this is what we call like a inverse scattering problem. So there are an infinity of solutions, potential solutions to this, because we are drastically undersampled. So we have to reconstruct these images and we have to fill things in. Now, before I tell you about that, a little bit about the teams that worked on this to do this, so a little bit of the sort of human side of this. So in July 2018, we all got together, a subgroup of us that are interested in imaging at the Center for Astrophysics at Harvard in the US. And we divided into 4 teams to work on taking that UV data that you saw and reconstructing it to produce an image. And there were 4 teams, and I was part of this team 3. So this was more sort of pretty much a European effort with 1 or 2 people from the US. And we were basically locked in rooms. We weren't allowed to communicate with each other for the entire week. And we all independently worked with that data using different reconstruction algorithms. I don't have time to go into those reconstruction algorithms, but effectively, you can look at, say, let's say you have a puzzle with 1,000 pieces and you throw away 900 of those pieces. How would you fill in the gaps? How would you go about doing that? So you could look at information. You could look at the correlations between neighboring pixels. You could look at the intensity of things, for example, and you could say, oh, things are brighter in the center and they seem to get dimmer further away. And there's different ways of doing this, and there are computational algorithms to do this. There are various methods. We have artificial intelligence algorithms. We have Monte Carlo methods. We have traditional algorithms like CLEAN that are used in the astronomical community, and many besides. And so each of us used different methods to do this. And at the end of each day, we showed only the results. We didn't explain how we calibrated, how we obtained these results. And on the 4th of the 5th of the 5 days we were there, I think our team and one other team got these images here, which are very similar. They're not completely clean, but they're ring-like feature. And we knew we were looking for a ring-like feature because, of course, that's what we see based on Einstein's predictions. And there are deeper reasons for that, but nonetheless, we're very happy about this and celebrating. And then the next day, we all gathered together and we stacked those reconstructed images. And we have the final image here, which is very close to what was published the next year in April. And so these are what the 4 teams obtained. And you might look at these and say, gosh, they all look so different. This is nonsensical, what are you talking about? But actually, if you look in the UV plane, if you look in the Fourier domain, they're very similar. And they're very similar in the sense that the brightest emission does indeed come from the south to the southeast. If you look in the visibility domain, there's effectively a blurred annulus of a certain diameter, which is proportional to the mass of the black hole, which is consistent, and many other things besides. And this is a linear scale, but actually, if you look at it at a logarithmic scale, you see more similarity as well. And this is what we obtain, and these actually are mathematically very similar to each other, even if they don't necessarily look visually based on this color scale, similar to our eyes. So we had a meeting just before the release at the end of 2018, where we figured that we were discussing how to disseminate these results, and we published in the end 6 papers in Astrophysical Journal. There's a special issue. 2019, it doesn't say 2019, we gathered in Hilo, Hawaii. So this is after we had this first result. And the reason we're there, I suppose, is because our budget's increased since this result. So, why not? And also 2 of the telescopes in the array are sitting at the top of this mountain, Mauna Kea here, which is obscured by the tree. So it was jointly hosted by the group there. And we meet regularly every year and always talking, and we meet every week, several times a week, discussing in various subgroups and so on. But anyway, back to the science. As many of us, there were 250 roughly at the time. I think we've since grown to 350. So when you're wanting to calculate these images, you have to construct an entire pipeline. And there's effectively four main ingredients. You have to model the black hole itself. You can say it's a black hole that is a solution to Einstein's theory. You need to model the dynamics of the plasma around the black hole. We've seen that. And you need to determine the radiation processes within that plasma and calculate the motion of the light rays. And then you have to fold all of this in the end of the EHT's configurations, all those different telescopes, what's the weather like, and so on and so forth. And you don't always get good data every year because sometimes the telescope doesn't work, the scientists couldn't get there because terrorists take them hostage, it's too cold to fly over there, you know, things like that. So it's actually quite tricky to get good data. So since 2017, we've only had good data again quite recently, in the last past 2 years. So I'm going to skip through all of this because I'm running out of time. But effectively, you can construct a pipeline that goes from theory, i.e. the theory of gravity, all the way through to a synthetic image. What we've done to infer physical properties of the black hole and its environment from these observations is feed in prior knowledge of the parameter space of the plasma and the black hole itself. And so we have prior mass estimates, for example, of the mass of the black hole. Some aren't so good, like gas dynamical measurements here, and some which are closer to what we infer, like stellar kinematics of motion of stars, for example, in the galactic center, and also of those nearby in M87 and of emission and absorption lines and so on. We get these sorts of constraints on the mass. And so, of course, there are error bars, and we take that into consideration. But in addition to the mass of the black hole, we also need to understand the geometry or the configuration of the source. So how are we looking at the black hole? Are we looking at it edge on, face on, somewhere in between? And it turns out that, that for M87, we're looking almost down its spin axis. So it's like we're looking, actually, as it happens, it's close to 163 degrees. We actually are, based on the sense of rotation, what we see, we're kind of looking up underneath it. And we see the jet itself as well points at a certain angle on the sky. It has a particular position angle. And that tells us the sort of orientation of the black hole itself. And those are constrained quite accurately in prior works. And we also have estimates. So when you want to calculate the spectral energy distribution, how bright it is at different frequencies, there are estimates, for example, in the X-ray, which is very constraining, that we have as well. And I won't go into that now. So when we have these parameters, we do things like general relativistic magnetohydrodynamic simulations, so like the swirling movies that I showed you earlier. That was just one realization, and there have to be many realizations. So you can control how rapidly the black hole spins. You can constrain the state of accretion. They come up with all these funny names. So this is standard and normal evolution. This is magnetically arrested disk. Sane and mad. There's actually a state in between called insane or semi-mad, and I don't put that there, but you know, astrophysicists, you know, we sit around in basements on computers a lot of the time, so we have to come up with these things. But there's all sorts of other stuff, physical processes that you can take into consideration. So you can consider the effect of cooling of the plasma and the ions. There's heating. You can consider the coterminous fluids, two fluids. You can change the actual theory of gravity and say, hey, what if Einstein's not correct? Which he might not be, right? There are things which can only be, which the general relativity can't explain. So you can look at black holes and other theories of gravity and so on. And then after this, you do what we call general relativistic ray tracing or radiative transfer, and you calculate the light that's and its motion from the source to the observer. And that's how you calculate these images and these beautiful movies that you've seen. And so you can construct, you have to put a lot of parameters in there, like the mass of the black hole, how much mass, say, per year it's accreting, it's swallowing, and various electron microphysics and geometry terms and so on. And there's much else. And so there are a few different codes that we use in the collaboration. And in the team that I worked in Frankfurt, we developed our own GRMHD code. And I also wrote a code since my PhD, which is one of the 3 codes that produced over 50% of the images in this library for M87. And we had to pool our resources because it costs a lot of computational time to do this. And so no one university, no one institute, no one country has available all the resources that we needed to do this in a very short time scale. So this was really a huge effort. And I should say that, this is of course not the work of one person. This is really, the work of many, many people sharing their research time over many years. And so you have these pipelines, and I'm going to skip through this. There's a lot of work that was done, and you can create libraries of black hole movies, basically like this. And each frame of those movies is a potential realization of the black hole, because you don't know what state, how turbulent it is. It could be in a flaring state where stuff looks really bright and it's accreting a lot of matter, or a lot of plasma is erupting and being launched away. It could be in a very quiescent or quiet state where not much is happening. And so this is why you need to look not just in terms of the properties of the matter and the light, but also the temporal evolution. Okay, now getting towards the end of the talk. There we go. So this is what we observed. And here's a movie that I made in time of this M87 black hole that fits the data in terms of inferred mass accretion rate, the mass, the distance, and so on. And this is what it looks like in time. And every frame in this movie is about 10 days of variability in the source. So the source varies extremely slowly, and this is just sped up. So every second here, every second here is 10 days of M87. And so you get these beautiful swirly movies. You've got this lensed ring. This is actually the light which orbits the black hole multiple times. This swirly stuff that's swirling around the black hole and falling inwards, falling onto the event horizon. That's the base of the jet and of the accretion flow falling in. But then in the end, we want to calculate a particular image which compares to this. And this is what it would look like if you had a perfect array with infinite resolution and you could observe forever. And when you convolve that with the actual finite resolution, so the beam size of the effective beam size of the array, this is what you end up with. And this is one which looks very similar to what we observe and fits those parameters. And in principle, you can create thousands of images like this. And so it's actually quite difficult to discriminate on the basis of images alone. But you can infer things like, for example, the black hole is spinning quite rapidly, for example. You see that there's a brightness asymmetry and it's much brighter in the southeast and so on. And so what we did, for example, before I wrap up, we looked at different states of accretion. We looked at different black hole spins, and we looked at different properties of the thermodynamics of the electrons which are producing this radiation. So on the left here, you see a sane model, and the black hole is spinning in a retrograde sense, and the electrons are concentrated towards the jet. In the center here, you see the same sane model, but now the black hole isn't spinning, and the electrons are focused more towards the disk. And finally, you see a mad one where basically everything's much more magnetized. And the black hole is spinning rapidly in a prograde sense, not in a retrograde sense. So it's like it's spinning clockwise or counterclockwise, and the electrons are concentrated towards the disk. And they all look pretty similar. And that's telling you that it's very hard to constrain just using these models on the basis of the total intensity. So 2 years later, let me skip over this. We did a lot of work to look at the position of the brightness, the bright feature here, the position angle, the flux, the asymmetry. So we're not just literally looking by eye at images. We have algorithms that measure, that do things like normalized cross correlations in structural dissimilarity indices and so on. And we work in the Fourier domain. But these are pretty consistent with the data. And actually, if you work in the actual sort of with the fundamental data in that domain, and you can plot these things, which are basically visibility amplitude plots, these data points represent this observation, and they're actually distributed in a hump-like structure. And this hump, if you look at this dashed line, this is actually the Fourier transform of a modified Bessel function. And this function that we've transformed is actually the analytic formula for an annulus, annulus being a ring with some thickness. And that ring is precisely the ring that you see in those images. And the diameter of that ring, Einstein's theory tells us, if the spin is low, or if you're looking almost face on, which is actually the case with M87, the diameter of that ring is proportional to the mass of the black hole alone. So you get an independent constraint based on how you fit this data of the mass of the black hole, not looking at stellar motions, not looking at absorption and emission lines, but actually looking at the strong field gravitational lens of light. So it's almost like a direct measure, not quite, but almost. And this is new, it's never been done before. And we get this new estimate of the mass. But actually this year we published some, in my view, much more exciting results, which I sadly don't have time to go into, about the polarization of the light. So you saw the previous image, But now this is a new one with these swirly patterns, and these swirly patterns show the polarization. And so what you're seeing here, you're getting a sense of the orientation of the magnetic field in the plasma there now, and you're seeing how it swells and the matter moves along those field lines. And this is what we're able to do. And we do that. Now, you're probably not going to be able to hear this, I'm afraid. But so let's skip that. But what we did is we were able to calculate the properties of the polarization of that light. And why is polarization important? Because the magnetic field in the plasma around the black hole leaves an imprint on the radiation in the form of its polarization state. And what we see are patterns like this on different days. So we observe for 4 different days. You see the swirly pattern with long ticks, which is the degree of linear polarization. And you see there's very little polarization because they're effectively dots in the northwest. And so you see the concentration of the polarization and linear polarization in the southeast. And actually what you're able to do with polarization, and you're able to get different measures, for example, the degree of linear polarization, the spread of the linear polarization. You can azimuthally decompose different annular radii of the image, and you can get different measures of this. And you can immediately rule out, for example, all the models in the lower row here are ruled out. And you can kind of see that because all of that magnetic field in these models is oriented radially, whereas what we observe is it's ordered azimuthally. And that immediately rules out lots of models. It preferentially selects models which are in a magnetically arrested disk state rather than a sane state, and so on. So it's very constraining. And I don't have time to talk about that, but if you have any questions, please ask me. So now to conclude, what have we learned so far? So the scales are enormous. So this is the M87 black hole to scale with our solar system. And so Voyager 1 isn't even past the event horizon of this black hole. It's so large. And there's a few sort of qualitative statements that we can make. So in that visibility domain I showed, you can fit the Fourier transform of a ring. We don't literally put rings on the images and measure them. We work with the actual data, and you get a constraint of 6.5 plus or minus 0.7 billion solar masses. And there's some systematic constraints, which are errors which are a bit smaller. And so this is an independent measure of the mass of the black hole, which is pretty cool. And it's consistent with previous observations. Now, it's not a wormhole. It's not some strange exotic object like a gravastar or boson star or something like this, because the angular size of objects like that are either too small or too large, or there's too much flux, or the asymmetry isn't right. So you can qualitatively rule out entire classes of alternatives to what this compact object would be. So you can't say it's 100% a black hole, but it couldn't really be much else other than something that is as compact as a black hole. And you see this central brightness depression where it's very dark. And it would be a lot darker if the instrument were better. And in time, this darkness depression, which is a factor of 10 at the moment, we're going to push to much higher, so dynamic ranges. And current EHT has a dynamic range of around 10. And I'm working in a project called the Next Generation EHT, where we're building a new array, which will also be based in space. And there you can achieve dynamic ranges of over 1,000 or more. And a lot of other objects, which aren't black holes, they have a finite flux here, whereas a black hole, it should formally almost be 0. And so you can, it's a smoking gun of a black hole because that's the event horizon. And you see a lot of variability from day to day. Now, even though this black hole changes quite rapidly, quite slowly, I said, for M87, it's of the order of days, hours to days, we see variation from day to day. And that's because what we're looking at here isn't the accretion flow proper, it's actually the lensing of the light. And so that's actually light that's orbiting the black hole multiple times. So you're looking here at light, which has been orbiting the black hole. And finally, just to say that I've said it already, but the size and the shape of this shadow is actually exquisitely sensitive to the fundamental properties of the space-time structure, so of the black hole itself. And so in principle, with better and better measurements, we can impose constraints. And so you can say, for example, that determining a mass that is consistent with previous measurements, actually, we've used Einstein's theory to determine that mass. And you could use other theories and you'd find stuff like wormholes don't work and so on. And so in a sense, it's a sort of soft test of strong field gravity in a decay hypothesis. And there's a lot of ongoing future work, which I can't go into here, but I'm very happy to talk about. But you know, the kind of simulations that we're doing, they are state of the art, but they are still limited, and there's always more physics to put in. Secondly, we have strong reasons to believe that Einstein's theory of general relativity is not the definitive theory of gravity. So we can't explain black holes on the scale of the event horizon, or on smaller scales, on quantum scales. We can't explain the large-scale structure of the universe, for example, and many things besides. And so there are a lot of people, including myself, who've written several papers on what would happen if this wasn't a black hole in general relativity, but in another theory of gravity, for example. And then we want to push to shorter and shorter wavelengths to get sharper and sharper images. We want to add more telescopes to the array, which is an ongoing effort that we're doing. And finally, ultimately, we want to put telescopes in space where we're free of the atmospheric constraints of our Earth's atmosphere, where we can extend those baselines beyond the diameter of the Earth, and where we can observe continuously. And I have some slides on that if people are interested. But to wrap up, I would say that this really isn't the end of things here. This is the beginning of a new era in measuring and studying black holes. There we go. And it is just the beginning. And there should be, I hope, a nice movie. And in time, we should be able to resolve better and better. So, thank you very much.